but this is part 2, which I was told has Pfaffians in it, because I voluntold you to say Pfaffians, all right? So, with that in mind, Herr Professor Dr. Christopher Voll will give us a talk on Pfaffians and other things.
Great, happy to oblige, James. Thank you. Thanks to you for turning up again to listen to me talking about tensors and enumerative algebra. So, what happened so far? I tried to summarize on this board on the left. Yesterday, I told you how tensors come from the corner of enumerative algebra that I make my living from. I introduced you to the class of groups T2, which are essentially class 2 nilpotent groups, which are as nice as they can possibly be. The derived group coincides with the center, so that allows us to identify the cocenter with a Z module free of rank A, say, and the derived group with a free Z module of rank B, say, and what all you need to know, or all you can hope to get from this group, it works both ways, is encoded in this commutator map that does what it says on the tin. It assigns to 2 residue classes modulo center of elements their commutator. Yeah, this is a bi-additive map, and as I learned yesterday, some people get away with calling this an AAB tensor. Yeah, so A into B. And I owe you a justification for bringing this up in the context of the counting problems that I was introducing yesterday. But before we do this, I called the commutator matrix of this commutator map the matrix that I get when I choose bases for these 3 modules Z to the A and Z to the B respectively. Such choices give rise to structure constants lambda I, j, k. Some speakers yesterday had all 3 in the subscript, but you've seen these things before, I think, in Yao Ming's talk. And that gives rise to a matrix of linear form, a square matrix, an antisymmetric square matrix of size A. A is green, yeah? This is green. Whose entries are linear forms in B variables. Yeah? And the coefficients in these linear forms are what drives this commutator map. Okay, now to something completely different. I told you what I call a counting problem. A counting problem is a pair consisting of a group, say, in this class of nice groups, together with a sequence of numbers that have the potential to interest some group theorist anywhere. And I introduced yesterday the sequence Rn tilde. Rn tilde is by definition the number of n-dimensional complex irreducible representations of G up to twist. If that tells you something, here it is. And if it doesn't, don't worry. It's a sequence of integers that some group theorists care about. What we do with the sequence is we use it to define a Dirichlet type generating function that we call the representation zeta function of this group G. It's built like the Riemann zeta function, but replacing the boring one by introducing these mysterious numbers Rn tilde. For reasons that are essentially trivial, this global zeta function enjoys an Eulerian product just like the Riemann zeta function. I can write this infinite sum as an infinite product indexed by the prime numbers of so-called local zeta functions. And these local zeta functions do the same as the global one does, just for powers of a fixed prime. Yeah? I will not go into the reasons for this multiplicativity. It's second-year algebra. But what we will do at the end of this lecture is we will somehow connect these local factors with the tensor that we get from the commutator map. That's my aim for today. Okay, how are we going to do this? I want to connect the commutator matrix with the problem of counting representations, and I will do this by quoting a theorem by Roger Howe from the 1970s. But before I do this, let me introduce a little bit of notation. Let me write for an integer n, a natural number n, let me write a non-negative integer n, let me write Wbn for the number of primitive vectors of integers modulo n of length b. So I mean so this is the set of x1, y1 up to yb in z modulo n to the b who are primitive, meaning that the GCD of these integers modulo n is 1. Yeah? There is no prime that divides all of the yi simultaneously. Yeah? So here I'm dragging, well, I'm not dragging you anywhere. I mean, you're sitting comfortably with your coffee, but I'm inviting you to come to a territory that may or may not be familiar to you. I mean, maybe you're used to working over fields. And maybe you're used to working over fields of character 0, character p, algebraic closed, whatnot. My experience says many people shy away a little bit when I talk about rings with 0 divisors. Here we are. Z modulo n is not a field in most cases, and so be it. Yeah, this is a finite set, obviously, of such vectors. And what we are going to do, and that's the key to connecting these two things, is we are going to feed the commutator matrix with vectors from this set. Please.
Is there a reason it has to have a parameter from a natural number? Why can't I just put any ring there?
You could put any ring there and find your bliss in this. What I will do, James, is I will take one of the elements in here. Absolutely, James. You can take any ring. What I will do is I will take such a primitive vector and I will feed it into the commutator matrix. Yeah, and as you say, I can do this with every ring. But if I do this, of course, what do I get? I get an A matrix, an A by A square matrix over this ring. And so far, James, nothing stops me from doing this for any ring. But for these kind of arithmetic rings, I can use what we learned, I reckon, in second year algebra, namely that these matrices, they have a nice normal form, namely the Smith normal form. Yeah? So what essentially the elementary divisor theorem is paid to do is elementary divisor theorem is this matrix may not be diagonal. Well, it isn't, yeah, because it's antisymmetric. But B is equivalent to a diagonal matrix, of course, also of size A, with entries n1 up to nb, where the ni's are divisors of n that divide each other successively. Yeah? So ni divides ni plus 1, and all the ni's divide n. So, and to say that these vectors are primitive is to say that certainly n1 is 1. Yeah? So, should we try this? No, we should not try this. I will not embarrass myself. You know this, yeah? You know this because you know the elementary divisor theorem. That's an integral matrix, and what I care about it are these elementary divisors. I do not just care about the determinant of this matrix. I do care about these elementary divisors. And I will tell you immediately why I do this, but first let's make an observation. Leveraging the fact that this matrix P is antisymmetric.
Can I just ask, equivalent here, is this equivalent modulo like the independent left-right action by GL Z or GL Z modulo?
Yeah, exactly. I'm taking the freedom to operate from the left and from the right with GLA Z mod n.
And possibly different ones, right?
Exactly. Yes. I just do what it takes. Yeah. So I have this matrix, and there is a least entry, so to speak. Yeah. I use independent row and column operations to get this least entry up here. Then I use it to clear the first row and column, and then I continue. Yeah. I think that's the exercise that our second years would have to do in order to internalize this. Yeah. So the ni's they divide each other. In a second, we will pass to p powers. So n1 will be a power of a fixed prime. So we will have something like p to the r1, p to the r2, all the way up to p to the rn. And the divisibility just means that r1 is less or equal to all the way up to Rn, and primitivity means that R1 is 0. Yeah? But globally, it works the same thing. So, why should we do this? Well, the matrix B is antisymmetric. B is antisymmetric. I don't know which of the speakers of yesterday it was so many, but at least one of them capitalized on the fact that the determinant of an odd-sized symmetric matrix is always 0, and the determinant of an even-sized matrix is always a square, and the square root is by definition the matrices Pfaffian. Yeah? So this chimes with the fact that will not surprise you that these ni's, they come in pairs. Yeah, they come in pairs. So let me write n1, n2 all the way up to na. Well, now you see we have a parity issue. I will brush this under the carpet. I will talk about n. No, what do we have? Yeah, it's an A by A matrix. Yeah, so this is an A. So they come in pairs. So let me write this as. Actually, let's not write this. Let's not make a fuss about this. So that n1 is equal to n2, n3 is equal to n4, and so on. Yeah. So what I need to connect this counting problem to this kind of matrix voodoo here is the following theorem, which I want to label Kirillov's orbit method. For the kind of groups we're looking at. And if this rings a bell with you, that's fine. If it doesn't, let me just tell you, there's a class of groups for which the representation theory is well parameterized by the action of the groups of the duals of their Lie algebra. Yeah? Some groups have nice Lie algebras. Wherever you have a Lie algebra, you have a dual space, just a space of functionals. And there's a natural co-adjoint action of the group on this dual. And sometimes when you're lucky, understanding the orbits of this action tells you something about the representations of the group. And that's Kirillov who pioneered this in the case of real Lie groups in the 1960s. And then people came along and extended this, call it a philosophy or a heuristic to all kinds of groups. And there's a volume in the Pacific Journal which essentially contains Roger Howe's thesis. Yes, it's 5 or 6 articles, and one of them I make responsible for spelling out how this works for nilpotent groups. Yeah, so you won't find this this theorem here in Roger Howe's thesis, but still morally. I mean, that's where I learned it from, and I didn't find an earlier reference. So what does Roger Howe tell us? Well, Roger Howe tells us something about the twist isoclasses of irreducible complex representations of G. Yeah, that's what I indicate with this tilde. This is the kind of stuff that we want to count. Yeah, and these representations, they can be sorted by what I would call level. I will not tell you what level means, but every one of these infinitely many twist isoclasses has a certain level. And now, Howe says, so these are finite sets, that's the point. If you want to understand this set of representations or class of representations, it's enough to understand for every natural number n, the number of twist isoclasses of level n, whatever that is, and now comes a theorem that says that this set of representations you can identify as a set with WBN. And you can identify it. So how does this identification work? Well, start on the right-hand side. Take a primitive vector modulo n of size b. Roger Howe tells you how to get a character of an irreducible representation of this thingy, essentially by plugging this vector into the commutator matrix. Then there is some induction that I will spare you. What I would say is that Roger Howe constructs a character of a representation associated with this y, and all we care about in our counting problem is the degree of this character. Yeah, the degree of the character is rho at 1, and this is it's a bit I should write it more prominently because it's so important. This is a function of these elementary divisors. So these elementary divisors, they divide each other. They're all divisors of n. I'll just write it down and then we'll talk about it later. This is the square root of the product of n over ni of y. So let me give you a chance to pass this. We start with a primitive vector, y, like this. We feed it into the commutator matrix. We get some antisymmetric matrix over this ring Z model n. Undergraduate algebra tells us that this guy has certain elementary divisors, b numbers that divide each other successively, and are divisors of n. So I can take this product, I equals 1 to a, of n over ni. Because this matrix is antisymmetric, this is actually a square and I take its square root. That's a number, that's an integer. And I want to draw a picture for you that helps me making sense of this number. Yeah? And for that I need to clear this board here. And if asking me a question helps you pass all of this, then I'll be happy to take it. Josh.
So that product in the square root
Yeah.
is a product of the quotients n over ni.
Yeah.
Right? It's not n over a product of the ni's.
No, it's a product
Right?
of the
Got
n
it.
over ni.
Yep. Thank you.
But I will illustrate this. So okay, so y, a primitive vector, gives us a bunch of integers, yeah? n1 up to na. They divide each other successively and they all divide n. Let me draw a picture. I love pictures. So this is a picture which I think of as essentially comprising a Young diagram of a partition that I'm going to show you in a second. And this partition fits into a box of size n by a. Yeah? So n is, you should think of as the level. All these representations, they factor over some principal congruent subgroup and that determines the level, whatever. That is the level, and A is the size of the commutator matrix. Yeah? And the ni's I want to sketch in like this. So n1 is 1. n1 is 1 and is equal to n2. Yeah? And then it goes up. So maybe I drew ni here. So what is this strange square root? Yeah, and they come in pairs, yeah? That's the point, they come in pairs. What's this square root? I equals 1 to a to I equals 1 to a, n over ni. This is, if you wish, the volume of this part of the picture that I'm drawing here. Yeah? N over ni is essentially what I see underneath this partition. These columns, they come in pairs, and I only take one of them if when they come in pairs. That's what this number here really is.
They come in pairs because they start with an antisymmetric matrix.
Exactly. They come in pairs because they come from an antisymmetric matrix. Yeah. So that allows how to define a polarizing subalgebra if you know how this goes. And that is somehow crucial, and that explains why this strange thing is an integer. Yeah. So, how this works exactly, I don't want to inflict on you. I want you to take home, well, not home, I want you to keep in mind now, we start with a primitive vector modulo n, we feed it into the commutator matrix, we do some undergraduate algebra to it, harvest the elementary divisors, we write them down, and knowing the sum of the co-elementary divisors is the degree of that representation. So, if I want to run over all representations and record their degree, it's the same as running over all levels n, running over all primitive vectors of this level. For each of the vectors, understand the elementary divisors type of this matrix, and just sum it up. Okay. I just made life easy for you. whether you notice or not, but that's good. Yeah, Josh knows what comes next. So the zeta function was defined as the sum over all twist isoclasses of representations. For each one, we keep track of the degree. Yeah, that's the same as what I just rubbed off. We run over all twist isoclasses. We keep track of the degree of the associated character. Roger Howe says this is the same as running over all levels. It's actually n, not n. For a fixed level, that's an infinite sum, yeah? That's an infinite sum. There are infinitely many natural numbers. If you fix a level, you have a finite problem. There are only finitely many primitive vectors modulo n. Finite problems are good, yeah? I mean, how hard can they be? And for each of these guys, you keep track of the degree of the character that Roger Howe's black box produces for this primitive vector at 1. And by his theorem, this is enough to really understand the square root of the product of the co-elementary divisors. Okay, this is good because this mysterious thing has become a linear algebra object. Yeah? So understanding this infinite series is the same as understanding the linear algebra of matrices over these finite rings that get larger and larger as L grows. Yeah? And I would like to spend a few minutes to tell you how this actually might, so how this brings in algebraic geometry. But before we do this, I think I want to honor my promise to tell you how to obtain the zeta function for the discrete Heisenberg group. Yeah? You remember yesterday I advertised the Heisenberg group as a very representable member of the class T2, yeah. And if you don't know what T2 is, the Heisenberg group you know, and its representation zeta function. I told you by a result of Magid and Nunley was nothing but the sum over the Euler phi values summed over all integers, natural numbers. Yeah? This was the theorem by Magid and Howe. And I suggest we prove this theorem together using, did I say Howe? I said I wrote, and I meant Nunley, Charles Nunley. Charles? So I suggest we test Roger Howe's statement that the twist isoclasses of irreducible representations come from these primitive vectors stuffed into the commutator matrix. Yeah, shall we do that? So, proof of this statement here. Hashtag. Proof of hashtag. Okay, now we do a computation. How do we do this? So Howe tells us we have to look at, well, we do it here. What was the commutator matrix with respect to the only sensible choice of bases? It was this here. Yeah, this is the commutator matrix. It's a 2 by 2 matrix with entries are linear forms in one variable. Yeah, it's a 2 to 1 tensor. And what does Howe tell us? Well, Howe tells us feed this matrix here with elements y in W1n and harvest the elementary divisors. Now, what is W1n? W1n are just the units modulo n. Yeah. So this is just units modulo n. How should I say this? Z modulo n star. Okay, so Howe says the zeta function of the Heisenberg group is obtained by, I'm glad it's literally the line above, I run over all levels n, and for each y in W1n, I evaluate the commutator matrix and I harvest the elementary divisors. But if y is a unit modulo n, that just means that this matrix here over z modulo n is the identity matrix, is equivalent to the identity matrix. Yeah? So what are the elementary divisors of the identity matrix? Well, here they are, 1 and 1. I said n1 is always equal to 1, didn't I? Said it, didn't write it.
You said it.
You said it.
Said it, didn't write it, and I'm still right. Yeah? I said they come in pairs. I said it and I write it, and it's still here. It's still true. 1 is equal to 1. Eternal truth. Very good. So n1 is equal to n2, and that's it. Yeah? Because we're done. Yeah? So this is n. So how does this stupid picture? Sorry. How does this picture look like? Well, now it's an n by 2 picture. Yeah? 2 is the size of the matrix, the size of the commutator group, and I'm drawing 2 columns and fill them up. And how tells me, yeah, well, you've drawn 2 columns, but you should only capture the size of this 1 column here. That is the degree of the representation that you get. For each unit modulo n, you get a representation, or a twist isoclass of a representation, of degree n. That's the size of that blue box. Very good. So I run through all of the units modulo n. Just copying what I'm doing here, yeah? I run through the units modulo n, and then I take the square root of the product from I equals 1 to 2 of n over 1. Yeah? So that is the square root of n squared to the minus s. Should I write n over 1 times 1? Does that help? Oh, n squared over 1. n over 1 times n over 1. Yeah? So. And that's good, yeah, because in particular, and that's I have to apologize, I mean 2 by 2 is really not very much space, yeah? There is not very much space for interesting elementary devices to develop, so that's all the same, yeah? So all I have to do is I have to count how many summons there I have, and that is essentially what the Euler-Phi function does for me. And the square root of n squared over 1 squared to the minus s is n to the minus s. And here we are. This was the statement. Yeah. So Magid and Nunley don't do it like this at all. Yeah, they just boss it out by hands. It's a text you can give to any bachelor student. Yeah. How do you define representations of this group of matrices? Well, you choose generators like we did, and you have to send them somewhere, and you have to make sure that the commutation relation is satisfied, and you enumerate this, and then you ask the question, if Josh and I have 2 representations, what does it take for them to be twist equivalent? And they work this out, and they come to this answer. What I want to advertise is, you don't need a bachelor student to know about representation theory. All you need your bachelor student to know is how to handle integral matrices. All you need anybody to know is how to handle matrices of linear forms. How hard can that be? So, I wanted to advertise also one bonus feature that you get by encoding your tensor data in this way. I said this en passant yesterday, I think. Representation growth has an asymptotic motivational as well. Yeah, people want to know how many representations are there, approximately. Yeah. So knowing that the zeta function of the Heisenberg group is zeta s minus 1 over s zeta s, let us say something sensible and interesting about this. Yeah? So a corollary of this equation here is that the number of representations of the Heisenberg group of degree at most n is asymptotically 1 over twice square root of 1 over twice zeta 2 times n. And that is the reason for that is, well, I could, so very rudimentary analytic number theory knowledge is used to get from here to here. And I won't teach you that morsel of analytic number theory. You can look this up anywhere. The zeta 2 comes from the fact that this guy here has an abscissa of convergence 2. Yeah? And at 2, zeta s converges. So this zeta value we see here in the constant of the asymptotic expansion. And I think this is interesting. Had you told me, had you just asked me about representation of this group, I wouldn't have gotten the idea to look for that zeta value coming in here. Yeah? So that's a bonus.
Isn't that factor something like pi squared over 6 or?
Yeah, exactly. It's so.
Yeah, so
Is
pi
this
squared
kind
over
of pi
Yeah, pi
squared over
squared
12 or something then?
That's it.
Yeah.
No, of course. But I mean, just
Yeah.
mentioning, just
Yeah,
mentioning.
there are formulae for certain things like this. I'm mentioning this because, Josh, for similar groups, we have expressions here in terms of other special values of Riemann and Dedekind zeta functions. And so certainly my knowledge is soon exhausted, but there are interesting formulae. As you pointed out that the most pi squared over 6 is that's zeta 2, yeah? So this is 1 over yeah, okay. So what I'm saying is that there are formulae for other special values of zeta, of Dedekind and Riemann zeta functions. Very good.
Don't you need zeta 2 over 2 rather than 1 over 2 zeta 2?
I don't care. Something like this.
Christopher, maybe you can zoom out. People are giving me numbers that I'm very surprised to see. So I'm going to look at this Heisenberg group. I'm
Yeah.
going to look at its twist representation, irreducible representation. And then I'm going to come away with something like pi squared over 12 times n. What am I looking at? What that number in the group? What am I really seeing? Is it obvious that there's that number associated to it? I don't see how there could be a constant times n coming from this at all. Like I don't know what approximation is doing here.
This is approximately, which means that
Is it just asymptotic?
yeah, g of n is approximately f of n if the quotient goes to 1. Yeah.
I see. So it's not constant because n keeps changing. So n can still be.
Well,
just that it approaches a
this is a
linear
constant
growth. Okay.
in front of this linear n,
Okay.
and it's an n to the 1, and not n to the 7 over 9
All right.
or 7 over Euler number.
So you keep adding the same number of representation. As n grows, you add a proportional number. I think I understand this now.
I'm looking at more and more of the representation. Yeah, this is twist isoclasts of representations of degree up to n.
But I mean, I would imagine that if I actually looked at the numbers, I would see really erratic behavior. Like for n equals
Yeah.
541, there'd be one number, and the next one would be erratically different. But you're saying that if I sum over them, I get this nice linear growth.
Well, in this case, I'm just reiterating what Magid and Nunley told us 30 years ago. If you look at the precise numbers, you see the Euler phi function. Yeah, but you're quite right. I mean, if you do this for more complicated groups, so in a way, I'm offering you an interpretation of the Euler phi function coming from tensor. Yeah, the Euler phi function is the number of matrices of this shape, over the units modulo n. Yeah, and of course, I mean, for this matrix, this is all complete overkill and nonsense.
Sure.
But I'm advertising the idea that these coefficients here, they are numbers of matrices of a certain elementary divisor type whose shape is given by the tensor.
Yeah.
That's the slope.
Are you missing a square?
Sorry?
I think you're missing a square. Because
I'm missing a square. I'm missing a square because we have abscissa of convergence. Thank you very much.
Yeah, I was
This is an n squared because the abscissa of zeta s minus 1 is at 2. I'm not missing a log term, so I write log n to the 1 minus 1, if you allow me, because the pole that this thing here is, there's a simple pole here. Yeah. Anyway, so there are general formulae, James, that allow us to describe the growth of the number of representations up to a degree as approximately n to the something log n to the something else times a constant.
Yes.
the something is the abscissa of convergence, difficult but rational. The something else is even more difficult but integral. And the constant is interesting, I would argue. The constant often involves special values of...
Is this an upper bound, or is this just, it can go either side of that?
It can and will go... No,
If you don't know, don't answer, don't worry.
It
I don't
goes on
want
both
to stop you.
sides.
it
goes on both
can
sides.
go all... Yeah.
Okay.
It's really what it says. It's an asymptotic statement. Martin.
Can you get like a situation where you have double logs and crazy stuff like that?
Double what?
Double logarithms or anything more annoying?
Something like
Log ends.
Yeah,
log ends?
yeah.
I'm
Not for a Heisenberg group.
not for the Heisenberg group, no. Let me say this, Valentin Blomer, mathematician in Bonn, and I, we are working on a paper refining these kind of estimates for groups of type A2. Yeah, so things like SL3, Z. You can ask similar questions. You get similar expressions by an analysis that is similar but much, much more complicated than for the Heisenberg group. And there, and Valentin is many things, but in particular an analytic number theorist, and he immediately saw how the explicit formulae that we wrote down for this allowed to discover kind of further poles. Yeah. So, and in that analysis, there are higher logarithm terms. So this is just a coarse approximation somehow how it works at the top.
But
Yeah?
this cannot happen with new Bolton groups.
I wouldn't go. So not in that leading term. In that leading term, we have n to the something log n to the something else. That's a theorem. Yeah. But what we could unearth when we go further left and left,
Oh.
that is completely uncharted for nilpotent groups. Okay. Let me clean the board.
Can I ask a quick question? Just
Please.
going back to I think you said that the WB, like the Y being primitive implies that in particular the BY, the entries of BY are also primitive. But I don't think this is true for an arbitrary, like, partially skew symmetric tensor B. Do we have to, like, I don't know, we could take, maybe a degenerate tensor, for instance, would allow us to break this. Maybe like the Heisenberg tensor, but we replace the Z with X plus Y or something.
You mean when we have a commutator matrix that had x or zeros or
Yeah,
something?
let's replace Y with Y plus X. And then I think we can maybe take n equals to 3, and then y1 equals 1, and y2 equals to 2, for
So
instance.
you take issue with what statement that I made?
That y being primitive implies by primitive.
I think this goes to the original commutator you defined, right? You defined it as G mod the center, mapping into the
Yeah.
derived
Yeah.
subgroup. And this is by definition not in the general.
I think what you're picking up on is, in the variables that I see here, how do I see this? I mean, primitivity is meant to make sure that at least one of these entries here, I find a unit p-adically, yeah? And I think that
But unless we restrict the, so far I've been thinking of BY. B is just an arbitrary anti-symmetric, partially skew-symmetric tensor.
Yes.
But maybe there are additional things we were asking of it, right?
I think I'm not asking more about the matrix. I do ask about the group. I do.
Isn't it because we are like assuming the derived subgroups and centers are equal?
I think this comes from the fact that B is not completely arbitrary matrix because the commutator map you want to be subjective.
Indeed.
And this is some strange property of B which is not so easy to describe, and that's what you're missing.
No, he just wants fully non-degenerate. That's all he wants.
Is that all this?
It's just fully non-degenerate. Yeah.
Thanks.
No, okay, you cannot have quite X plus Y.
That would not be full, as Pete described it yesterday.
Okay.
Yeah, x plus y is not.
It wouldn't be full. You'd have a three-dimensional commutator, rank 3 commutator rank 2 commutator rather than a rank 1 commutator.
I would have a two-dimensional center, wouldn't I?
I mean, the definition you wrote at the very beginning wouldn't make sense. It would break.
Okay. Can we agree that there are some natural non-degeneracy conditions on B that justify me in making this assumption? And you're, okay. So the general situation is not like this, but it's easily reduced to this. So that's what I want to make. dear. So we have this description of how of irreducible characters, rather than twist isoclasses, in terms of this. So the question is, how do you go about this? Yeah. So let me rephrase Howe's result and saying en route define some notation. Okay. So what I want to do first, I want to localize. So I just said that the zeta function of G is the product of local zeta functions. This is essentially because nilpotent groups are nilpotent, and finite nilpotent groups are the products of their pseudo p subgroups, and representation theory is multiplicative over direct sums. I will not say more about this. It's really not so difficult. So let's focus on a prime p. Let's fix a prime p. Well, we fix it, but we keep in mind that we have to vary it later. Yeah. So, but for the moment, let's fix it. So this whole game here, or this whole board, I could now kind of localize. Yeah. So rather than talking about an arbitrary natural number n, I would talk about a power of this prime, and primitivity would mean that this vector is not 0 modulo p, for example. But the same would hold. So let me introduce notation. Let me define as n. Oh goodness. N L alpha p the following. So first I should say what alpha is. So so what I'm going to do now is I'm looking at the situation, yeah, where n is p to the l. So this level is now encoded by this exponent l here. What is the vector of elementary divisors look like? Well, I said they came in pairs. I still say this, and I want to call the numbers that occur here, which are p powers, as alpha 1, all the way down to p to the alpha a half, p to the alpha a half. Yeah. So this is a vector of size, right? It's a vector of size a. Yeah. And okay, a may or may not be even. I don't really care. If it's odd, then we add a 0 here. I'll just restrict to the case that a is even. There's no real restriction. Yeah. So all that alpha does is to harvest, so to speak, the a half integer exponents of the elementary divisors, and of course we get a partition. This way we get a partition alpha 1, alpha 2 down to alpha a half. Let me indicate that these numbers are non-descending by this symbol, and the primitivity means that alpha 1 is always equal to 0. Get this picture up again. Now I'm drawing a box of size L times a over 2, and I fit these numbers alpha in alpha 1, alpha 2, alpha 3. Maybe I hit bottom at some stage. How tells me that I care about this volume here, so to speak. Full non-degeneracy means alpha 1 is 0, so I certainly have something that is at least L, yeah? And that makes sure that these numbers grow as they should. Okay, NL alpha p, what's that? That is the number we want to count. Remember, in the baby example of the Heisenberg group, I concluded, well, all vectors give the same thing. How many vectors are there? Euler phi of n. In general, it's more complicated. You give me a level L and a partition that you want, and you ask me how many vectors, how many primitive vectors give rise to a matrix of that form given by the tensor that have these elementary divisors. And the answer is, by definition, NLP alpha p. So, slowly, this is the number of vectors y in z modulo p to the L to the b, which are primitives, so which are not divisible by p, such that the commutator matrix evaluated at y is equivalent to the diagonal matrix p to the alpha 1, p to the alpha 1 all the way down to p to the alpha a half, p to the alpha a half. That's a finite number, yeah, because this is a finite set. And knowing this number is as good as knowing the zeta function. That's what Harm essentially tells us. The zeta function of our nilpotent group, you can write as an infinite sum over all levels, locally at p. You run over all levels. For a fixed level, you run through all elements that are non-degenerate, modulo p to the l, all vectors that are non-degenerate, modulo p to the l. We'll write this p to the l. You count how many give you a fixed elementary divisor type. No, you just run over all alphas. Yeah, you run over all alphas, and now you count how many vectors there are that give you modulo L elementary divisor type A. And once you know this, you know the degree of these things. That's just the volume under here. And what's that volume under here? That's the sum I equals 1 to a half L minus alpha I.
Christopher,
Bitte?
I'm missing some piece of the data here. Why is this n not just a tableau or something? Is there something more going on here?
Why is that n just a tableau?
This picture you keep drawing,
Yeah.
I could mistake this as a young tableau, perhaps.
You could see it as a young tableau and you would not be mistaken. What I'm drawing here, James, is the young tableau of the partition alpha.
Yeah.
This is alpha 1, which is 0, alpha 1, alpha 2, alpha 3, and so on. This is the young tableau of the partition alpha. And what Howe tells us to care about is what's underneath this young tableau in this box.
But what does underneath mean? What's in the shaded region? Are there numbers in there?
That's what it means.
It just means the
So-
volume. So I'm just counting the total number of boxes.
You are, James, you're not just fixing alpha, the partition,
Yeah.
you're also fixing a level, which by definition is at least as large as the largest part of alpha. Yeah? So that's the two data that you have. You have alpha and a level. Alpha is yellow. What else? And L is what's that? Purple. So you run through, you fix alpha and the level. Alpha is what I see up here. That could be any partition. That partition doesn't know anything about L.
Okay.
But L is also there. And what Howe tells us is, with these two data, whenever you have a vector that gives you these two data, you get a representation whose degree is given by this quantity.
And that's not just some tableau as well? I mean, couldn't I just see it as a tableau?
You could see this as a, sure, you can look at
Double tableau
yeah.
where parameter L tells you how large it could be.
Yeah.
I don't, there must be some name.
It depends a bit what you want to fix and what you want to let go to infinity,
I
yeah?
see it now, I understand it. The point is
Yeah.
that alpha could have stopped somewhere, it could have been all flat. L could have been really long.
Yeah.
Okay.
And you could also now play games as kind of fixing alpha and letting L go to infinity.
Right.
Yeah. And maybe that picture isn't the idea, because I mean nobody precludes that
So there's more than a tableau in here, I understand.
I could have that. What I can't have, and I think that addresses your question, I can't start down here. Yeah, so I'm guaranteed that this representation that I get has a degree at least L. Yeah, and that's important for this sum to be well defined. Ah, fuck. Sorry. Good. Now that's easy, right? I give you finite data and I ask you to compute how many vectors there are. I mean, a computer could do this, couldn't it? No. Now, okay. Now my job is I want to really shut up, but no, I don't want to shut up. How do I do this? Okay, I give you 2 hints as to why algebraic geometry helps us. How about that? And then I shut up. Yeah? Good. So, so the overall question that I hope to address with you tomorrow, if you bear with me tomorrow, is how to compute this effectively. Well, effectively, or at least effectively / conceptually. Yeah? How to compute these numbers. And I put computation in inverted commas because I'm also liberal as to what you want this to mean. You see, the point is, if you give me a fixed L and a fixed alpha and a fixed P and a fixed commutator matrix, then yeah, if the size is reasonable, probably we could ask a computer to do this. But the point is, we have to run over all L. We have to run over all partitions. And we want to, and that's important, an important point that I will make tomorrow, I said fix a prime P, but I also told you don't fix it. Yeah? We want to do this with the variation of the prime in mind. Yeah? We want to remember that we have to do this not just for 2, 3, 7, and whatever comes after, but for all primes simultaneously. And that's somehow where a lot of subtlety and beauty is hidden. Anyway, so 2 sub-questions to give us, to fill the awkward silence when we have coffee. 2 questions. What does it mean what does it mean that alpha is 0? What are we counting? What are we counting? Not if, but for alpha equals 0. Well, and at the risk of having really awkward silence later, I'll answer this question now. To have alpha equals 0 means, well, it means that that everything is orange, yeah? Everything is orange. Alpha is 0 means how it tells us to compute the size of this. But what does that mean for the commutator matrix? Well, it means that it's invertible. Yeah? Alpha is 0 means that all the alphas are 0. That means that our commutator matrix is equivalent to the identity matrix. Yeah? I can bring it into identity form by multiplying with an invertible matrix from the left and maybe another one from the right to get it into identity type. That means it's invertible. Yeah? So for alpha equals 0, we are counting. What are we counting for? Well, invertible. We are counting the y's such that by is invertible. How do you do this? Well, if you want to count things that are invertible, and you know how many things you run over, you could as well count the y's for which this is not invertible. And when is a matrix not invertible, now we come back to our first years, they should know that this is the case if and only if the determinant vanishes modulo p. Yeah? So this is a hint as to why this problem here is connected with counting points on Pfaffians. Yeah? So whenever the Pfaffian vanishes, does not vanish modulo p, has no, okay, if the Pfaffian has no roots modulo p, that means for all of these y's, by is invertible. This is just the total number. That's just the size of WBP to the L. Yeah? And somehow how much other alphas get reflects how invertible the commutator matrix is. And to make this precise, I make my job for tomorrow, and I thank you for your time with me today.
I thought you advertised 2 questions, Christopher. Isn't that just one?
Sorry?
I thought you advertised 2.
Oh, thank you. Thank you. You didn't have to do this, you know. The other question was, to remind me now. Yeah. There were other questions. The other question was, and for that I have to draw my picture again. And that brings in determinantal varieties, not just the determinant. So a version of that picture was that. So we have alpha going down here. And let's say this here is alpha I. Yeah, this quantity here is alpha I. What does it mean that this alpha I is a certain quantity? Well, you remember the matrix By was equivalent to p to the alpha 1 twice, and so on. So at some stage we get p to the alpha I also twice. Yeah. So what does it mean that our y gives us a by such that this occurs here? Well, you will agree with me, I think. Don't see how you cannot. That this quantity here, this quantity, I can write as the difference of two quantities. Josh knows what's coming. It's the difference between this quantity and this quantity. Yeah? The width, the size of this column here is the total volume of this guy minus the total volume of this guy. And why should I care about this? Well, I'm having trouble encoding. No, I'm not having trouble. I'm telling you. Here's a way how to encode elementary divisors in terms of algebraic geometry. Ideally, we want to see these alpha i's as p-adic valuations of certain polynomial maps. Yeah? And we can. Alpha I say, is the difference of the vanishing degree of the I plus 2i plus 2i minus of the matrix minus the vanishing degree of the 2 to the I minus 1 times 2 to the I minus 1 minus of B. Yeah? So we have B, that's our matrix B. To compute alpha I, that's an A by A matrix, yeah? To compute alpha I, what I'm saying is we have to look at all the 2i by 2i principal minus, remember this is an antisymmetric matrix, but knowing the valuation of the vanishing degree of the ideal generated by these minors is not enough to understand alpha I. The vanishing degree of the polynomials defining this ideal give me this total volume, and to get this difference here to speak, I have to subtract the vanishing degree of the polynomials defining the 2i minus 1 by I minus 1 minus. And that's where the algebraic geometry comes in. So what I wanted to do today was the following. I wanted to recall that the groups that I care about are essentially given by what I call commutator matrices, antisymmetric matrices of linear form satisfying some non-degeneracy condition. And I showed you how Roger Howe told us that understanding the elementary divisor types of these matrices as we run over all integer substitutions for the variables allows us to say something non-trivial about the representation growth of these. And what I want to do with you tomorrow is I want to at least hint at a tool bag coming from p-adic integration, that was the adjective missing here, that allows us to do these kind of considerations in a somewhat explicit / algebrogeometric way. And now I really do shut up.